Hello everybody, this is the second video clip for chapter 7. Okay, from the previous one we know that in order to determine whether the function is Riemann integrable or not, okay, we are going to find any partition, okay, possible, and then finding the lower sum and the upper sum, and then looking for the lower integral and the upper integral, whether they are the same or not, okay. And that one sometimes it will be very difficult, okay, when you work with some function that it is difficult to determine the supremum or the infimum of the function over some closed interval, okay. So this video clip will give you some criterion, okay, that is actually workable, and it will be a criterion that we are going to use several times in this chapter, okay. This one is called the Riemann criterion for integrability, okay. So we are going to have your f as a function from the closed interval a b to the real number r again, okay. This one is already bounded function. Then your f is integrable on this closed interval a b if and only if, okay, no matter how small the epsilon is, we can find a partition depends on this epsilon, so that your upper sum of this partition and the lower sum of this partition, the difference between them is less than this epsilon, okay, it's less than this epsilon. And actually, I mean, from this one you can interpret in other words that if you can find a partition which is depends on the uh, positive integer n, okay, such that the limit of a difference of the partition, I mean a difference of the upper sum and the lower sum of the same partition goes to 0, okay, then your f is integrable as well. And these limit, I mean either the limit of the upper sum or the limit of the lower sum will be the same, and it will equals to uh, the value of the integral of this function f from a to b, okay. So let us prove this criterion first, and then we are going to also prove the corollary, okay. So for the criterion, so that you can use this one to perform any Riemann integration for some other function, okay. So because it is the if and only if statement, so let us do p implied q first, okay. For this one we are going to assume that your f is integrable, okay, over the interval from a to b, okay. So it means that your lower integration and the upper integration, they are the same. This one just come from the definition, okay. So we are going to prove this statement with the for all. So we are going to let any epsilon given positive, okay, and we using, I mean, don't forget that the lower integration and the upper integration defined as a supremum and the infimum, right? So since this one, just recall, okay, it is a lower, right? It will be in the opposite way, right? It will be a supremum of all the lower sum, right? Where p is a partition, okay, of the closed interval from a to b, right? So what does this mean? If it is a supremum here, okay, here is your LF, right, the supremum. So it means that if you subtract your supremum away by epsilon, then you can find something that is I mean something in this set, right, some element in this set that is bigger than this supremum minus epsilon, okay. However, I mean instead of only epsilon that you are going to subtract, okay, we are going to adjust a little bit by epsilon over 2, because we are going to work on the lower integral and also the upper integral. Okay, so because they have two they got two ways, so each one of them will depends on epsilon over 2. Okay, so it means that now we can find a partition, let's call P1, okay, of this closed interval AB, such that your as we told you, the lower integration and subtract away by epsilon over 2 will be less than your lower sum, okay, of this partition and a function f. Okay, so on the other hand, because your upper integral, it is defined by the infimum, okay, of this upper sum, okay, your p again, they are partition of this closed interval a to b, okay, and by infimum, so it means that the infimum is right here, okay, so let's use it as a u, and then if you add a little bit, okay, if you add your u a little bit by epsilon over 2, okay, you are going to find an element in this set, okay, that is sit here, right? So it means that there is another partition, let's say P2, okay, it may be a different from P1, such that your u added by epsilon over 2, okay, so it is not the infimum anymore, right? So this one will be greater than or equals to 1 upper sum, okay, taking with this partition. Okay. So what is it that we have learned from the last video clip? Okay, using, like, if you got two partitions like that, you are going to use a refinement, right? So we let your p epsilon becomes this p1 and p2. Why is that you can say that this p1 and p2 depends on epsilon? Because you see here, this one, the p1, it is given by this negative epsilon over 2, right? And the p2, it is also given by this epsilon over 2. So the union of p1 and p2 can be regarded as the p epsilon. Then by this one, we know that the lower sum, okay, take away the epsilon over 2, it will be less than the, oh, I'm sorry, this one will be strictly bigger than, sorry, this one will be less than your p1f, okay, we just use this relation, okay, just put it here, okay, but for the refinement, okay, use a refinement, the lemma about the refinement, this one will be less than or equal to the p1 union p2 partition, right? Okay, and use a definition of your lowest sum and the upper sum. This one, of course, will be less than or equals to the upper sum. Okay, use the lemma again about a refinement. Okay, this one will be less than or equals to the p2, okay, only one of them, okay, instead of a union. And then this one, okay, use that relation over here. You see, your upper sum of using the partition p2 will be less than the upper integral and added epsilon over 2. Okay, so it means that if you just consider these two things, okay, because this is what you need to prove, right? So it means that your upper sum of this partition depends on epsilon minus the lower sum of this partition, okay, it will be less than, it will be less than what? The upper sum of this one, okay, minus the lower integration subtract away by epsilon over 2, right? Okay, so you just first use this relation, okay, but using multiply by a subtraction first, right? Okay, so this one will be the other way around. Okay, okay, so it will be bigger than here. Okay, you see this one is bigger than this negative. All right, and then you use this inequality as well. This one, your u is less than, the upper sum is less than the upper integral plus epsilon over 2, right? So you use this one with this u p epsilon, so it will be uf added epsilon over 2, and then subtract this one, just leave it as it is. Okay, however, these two, the upper integration and the lower integration, because your f is integrable, so they are the same. They will cancel, right? And these two epsilon over 2 will combine and become the epsilon. Okay, so you got what you need, which is the difference between the upper sum and the lower sum of a particular partition p epsilon will less than the epsilon given. All right, so this is what we have. So on the other hand, okay, for q implies p, so we are going to let epsilon positive by assumption, because right now we are going to assume that for each and every epsilon we can find a partition, right? So there is a partition of this closed interval depends on epsilon, okay, such that your difference of the upper sum for this partition and the lower sum for this partition less than the given epsilon. Okay, and from the definition, okay, your lower sum of one partition will be less than or equals to a supremum of all partition, right? So this is a definition of your lower integration. And on the same token, your upper integration will be less than, this one is a supremum of all upper sum, right? So this one, is an infimum of all upper sum. So this one will be less than or equals to upper sum of one partition. Is it? So again, this one is also from the definition. Okay. So it means that if you use your upper integration subtracted by your lower integration, this one, from this relation first, for the first one, it will give you the u p epsilon f, okay, and by the second assertion, the second relation, but you insert the negative first, so this one will be reversed, right? So it means that the negative of the lower integration is smaller than the negative of your lower sum of this partition. So it means that you got this relation, right? The same inequality here. However, this one, from the assumption, it is less than epsilon. All right, so what does this mean? For each and every epsilon, no matter how small, you can have the relation that these two real number less than this epsilon. So it means that it implies that your u and your f cannot be something else, okay, but they should be the same. So the upper integration and the lower integration are the same, and your f is intractable over this interval from A to B. Okay. Okay. Now, so we have this one. So it means that later on, in order to determine that your f is intractable, we are going to just find a partition depends on the epsilon that your upper sum of this partition and the lower sum of this partition is not that far away from this epsilon given. Okay, this is what we are going to use in order to say that your f is intractable. Now let us just a little bit go over the proof of this corollary. Okay, so instead of depending on the epsilon, we are going to depend on the positive integer n, and then later on we are going to let your n goes to infinity and make a difference between the upper sum and lower sum goes to 0, okay, as your n is larger and larger. All right, so for the proof, okay, so this one is the proof of the corollary 7.1.5. okay, because we are going to prove that this one will implies that your f is intractable, right? So we are going to let your epsilon positive, okay, then by the limit, okay, since we have this assumption that your upper sum and the lower sum depends on this one equals to 0, okay, by this epsilon and the limit goes to 0, we can find the positive integer n such that for each and every n, okay, that your n is greater than this capital N, the u, p, and f, let me just write down here, the upper sum of this partition subtract the lower sum of this partition, okay, under the absolute value less than epsilon. Okay, actually this one minus 0 less than epsilon. Okay, however, I mean this one, because your upper sum always bigger than your lower sum, so it means that you don't really need to have the absolute value, and because the limit equals to 0, so this one can be shortened by this, right? And what is it that we need actually for the theorem? The theorem saying that you just need only one partition, right? Only one partition that this inequality occur. But right now, actually you got several partition because your Pn, okay, this partition Pn, okay, it can be, I mean, it can have this property for each and every n that is bigger than or equals to that capital N, right? So it means that in particular, because we need only one of them, right? In particular, if you use your small n, okay, replaced by this capital N that you have exist here, so you got this partition, okay, for the capital N, I'm sorry, this is L, a lower sum for this particular capital N will less than epsilon, okay, will be less than epsilon. So from the theorem 7.1.4, your f is intractable over this closed interval from A to B, okay, and you got this corollary. All right, now let us apply the theorem as well as the corollary to determine this integrability of this function, okay, whether they are integrable or not, and if it is integrable, then what is the Riemann integral of this function, okay? And you may really need to have this kind of formula, okay? The first one is a summation of k from 1 to n, which will be n plus 1 over 2, and then a summation of k square, okay, from 1 to n as well, it will be n plus 1 to n plus 1 over 6, and the summation of k cube from 1 to n, it will be this one and then just square. Okay, so the first one is a function, I mean the identity function, which is pretty easy, fx equals to x. Okay, so what is the thing that we are going to use? We are going to use the corollary. So by the corollary, then it means that we are going to define one of the partition, right? This one is a partition of this interval from 0 to n, which is depends on n, and later on the limit as your n goes to infinity of the upper sum, okay, subtract by the lower sum for this partition equals to 0. So the one that I mean the most easiest one is that we are going to divide this one into equal subinterval, right? So you are going to let the length of this interval, it is 1 minus 0, right? And you are going to just divide it by n, so that each of the subinterval, of a subinterval, okay, will be the same, and it is 1 over n. So your partition will be starting from 0, 1 over n to 2 over n, etc. up to the one before the last, it is n minus 1 over n, and the last one will be n over n, right? So this one be a partition, okay, of this interval from 0 to 1. Okay, that's pretty simple, right? So for each I, okay, which is starting from 1 2 3 etc. to n, okay, your mi, which is a infimum, right, of a function f of x, okay, whenever your x it is in the closed interval I minus 1 to xi, okay. However, your function f is simply the x, right, and the function the identity function, it is actually increasing, so the infimum will be the left endpoint, is it? It will be the left endpoint, okay. So this one, let me just elaborate it a little bit. This is x, okay, whenever your x it is actually in the closed interval from I minus 1 over n and I over n, right? So if you want, you may draw the curve, okay, this is y equals to x, and this one, it is the subdivision, right? For example, this is 1, this is 0, okay. So for example here, let's say that this one is I minus 1, okay, the left end of the nth subinterval, and then this is I over n, okay. So the here will be your infimum, and of course there will be your supremum, okay. So this one, the infimum, okay, it will be your small mi, it will be I minus 1 over n, and your supremum of each and every interval for this function value, okay, because it is again the increasing function, so the supremum will be the right end, so it will be I over n, okay. So if you have your small mi and capital Mi, you can immediately calculate your lower sum, which is your mi and then xi minus xi minus 1. However, this one, each and every subinterval, the length is 1 over n, okay. And don't forget that the parameter that is running, the branding parameter, is only the I. Your 1 over n actually is a fixed parameter, so you can move out from your summation, and you are going to have 1 over n and summation from I from 1 to n of I minus 1 over n as well. Okay, so again, this one is another fixed parameter, so you can move out as well. So the thing that we have left is only a summation of I minus a summation of n. Okay, so the summation of I from 1 to n, we already have it over here. So it is your n plus 1 over 2, and then a summation of 1 n times. Okay, so it will be just subtract away the n, right? Okay, and don't forget that you already have 1 n here and 1 n there, so you are going to divide by n square. Okay, you're going to divide by n square, and you can maybe, if you want, then you can simplify this n cancelled, right? And then you end up with n minus 1 over 2n for your lower sum. How about your upper sum? Okay, your upper sum will be the same thing, but maybe a little bit simple. Okay, so this one again, your capital Mi, and then multiply by the length, right? The length of each interval, which is again 1 over n. So your 1 over n will pull it outside. Okay, so to have what, 1 over n, and then your capital, it is I over n from 1 to n. So your n is another fixing parameter, so you move it out, so you got n plus 1 over 2n square, right? Or I mean, this one cancel, so you have n plus 1 over 2n. Okay, so what you are going to measure, you are going to measure the difference between the lowest the upper sum and the lower sum, and taking the limit, right? So it means that the limit as your n goes to infinity of this upper sum, and the lower sum becomes the limit of n plus 1 over 2n minus n minus 1 over 2n. Okay, so the n cancelled, right, and the one combined, so you got a limit of 1 over n, which is 0. So it means that this limit goes to 0. So by corollary, this function is integrable, okay, over this closed interval, and the integration from 0 to 1 of this is actually either the limit of the upper sum or the limit of the lower sum. Okay, so let me just use a limit of the upper sum here, which is n plus 1 over 2n, so you got 1 over 2. Okay, so this is the integration value of this function fx equals to x. Okay, the identity function. All right, so the next one that you may think of, okay, but actually it is not that difficult as well. Okay, it is the function f of x, but this one, let's say that here you got from 0 to 2. Okay, from 0 to 2, I'm sorry, this is a typo. Okay, your x start from 0 to 2. Okay, but your function f of x, it is x square. Okay, and this one will be 8 over 3. Okay, to show that this integration equals to 8 over 3. Okay, so we are going to do the same thing, calculating the lower sum, okay, of a partition and the upper sum of a partition. Okay, and a partition that we are going to talking about, okay, it will be a partition of this closed interval from 0 to 2, okay, which is the length, this time the length of subinterval, will be still, let's say 1 over n. Okay, so it means that your partition will start from 0, 1 over n, 2 over n, just use the same thing. Okay, n plus 1 over n plus 2 over n, and then up to like n plus n, so becomes 2n over n, which equals to the left end of this interval, which is 2. Okay, so now you have 2n subinterval, right? Subintervals. So it means that for each I, which is running from 1 to 3, etc. to 2n, what is your small mi? The infimum of this function value whenever your x it is in I minus 1 over n and I over n. Okay, so this is pretty much the same as what we have previously. Okay, however, instead of a straight line you got a curve, but this curve, okay, from this one to the right, okay, it is still increasing. So right here on your left end it will be your smaller mi, and on your right end it will be a capital Mi. Okay, so this one it is simply what I minus 1 over n and then square, right? Because don't forget that right now your function value got a square as well. So your capital Mi, the supremum of x square, whenever your x it is in this subinterval, okay, it will be your right end value, which is I over n square. Okay, so from your capital Mi and a smaller mi, you know how to calculate your lower sum, which is a summation of this one and then the length of each subinterval. Again, this length it is an equal length of 1 over n, and this one you need to be careful because your I, you got 2n subinterval, so it need to start from 1 to 2n. Okay, this one your 1 over n again can take out. Okay, so here you got 1 over n, I from 1 to 2n, and your smaller mi it is I plus I minus 1 square over n square. So again your n square can take out as well. Okay, so if you want to calculate this one, it depends on how good your algebra is. Okay, so if you are not so sure about your algebra, then you may say that this one is actually summation from I to 2n and then I square minus 2i plus n plus 1, right? So a summation will be distributed into each and every terms there. So you are going to have 1 over n cubed, and then the first one a summation of I square. Okay, so it will be, however, you need to be careful when you use this formula. This formula it goes to n, right? But this one instead of the end point is n, the end point is actually 2n. So each and every n here will be replaced by 2n. So you got what? 2n, 2n plus 1. So instead of n plus 1, 2n plus 1. So it will be like this. Okay, and then over 6. This one as well, the 2 can be out, right? And the summation go to summation of I, but the end point is 2n. So you got 2n plus 1 over 2, and the summation of 1 for 2n times. Okay, so it will be 2n, not 2n times, is a 2n's copy. Okay, 2n copies. All right. So here this is the lower sum. Just leave it like that first because that is too complicated maybe. How about your upper sum? Your upper sum, it is simply from a summation from I to n of a capital Mi and the length of each subinterval, which is again 1 over n, right? So your 1 over n can be out, and then this one, it will be a summation of I square over n square. So your n square can be out as well. And don't forget that the end point here is 2n. So you got n cubed and then a summation of I square. Okay, so it will be 2n plus 1, 4n plus 1 as well over 6. Okay. So it means that if you want to find the limit of a difference between your upper sum and the lower sum, okay, the remaining, because you see that you got this same term over here and over there, right? So after do a subtraction, the remaining will be all these terms left, right? However, don't forget that you still have n cubed and you also have this negative, so it will be 2n plus 1 over the 2 and the 2 cancel, right? Over n cubed and minus 2n, right? Okay, this one you have negative. Okay, so here's the n square and this one's n cubed, so it will goes to I mean, actually, if you want, this one is actually can be simplified into what? 4n square and right, it's only 4n square, right? Because the 2n and the 2n cancelled over n cubed. Okay, and it is a limit of 4 over n, which is 0, of course, right? So it means that by corollary 7.1.5, this one is again integrable over this closed interval from 0 to 2. Okay, I'm sorry, that's a typo. It is 0 to 2. Okay, and the integration value, okay, it is depends on whether the limit of L or the limit of U. So for this one, we are going to use the limit of U. Okay, the limit of your UPN. Okay, so here the limit, because you got n cubed on the bottom and also n cubed on the top. Okay, so you just collect all the coefficient, okay, of the largest power, which is 2, 4, and then on the bottom is 6. Okay, so your 2 and your 2 there will cancel, so you end up with 8 over 3. Okay, as what we needed here. All right.